You have an active infrared night vision device. In front of you is an enemy dancing. This device uses an S1, S20 photocathode to convert photons into electrons. However, because it is extremely inefficient and only sensitive to infrared, it requires an infrared searchlight to illuminate the target, which then reflects back into the goggles. When infrared light hits the photocathode, it knocks out electrons, which are then accelerated by high voltage to bombard a green phosphor screen, producing an image sensitive to the human eye. You shoot and kill the enemy, but little do you know, you've already been targeted by another enemy in the dark. This enemy is using a first-generation passive, low-light night vision device. It utilizes a multi-alkali photocathode that can easily kick out electrons even from weak visible light, like moonlight or starlight. To enhance the image, it combines 3 image intensifier tubes, a high vacuum acceleration zone, and a fluorescent screen, all connected via fiber optic panels. While it amplifies faint light tens of thousands of times, the curvature of the tubes causes severe edge distortion, and the bulky, multi-stage design makes it very large. Furthermore, its short detection range leaves you blind to the enemy, and he shoots you dead. Moving on, another enemy appears using second-generation night vision goggles. This device uses a new S25 photocathode and a microchannel plate, MCP. The S25 cathode is highly sensitive, and the MCP is packed with millions of tiny, tilted glass tubes coated with a semiconductor material. When electrons enter these channels, they bounce off the walls, triggering secondary electron emissions at every impact, eventually multiplying the signal exponentially. This design is compact, and it includes automatic voltage regulation to dim the brightness if exposed to sudden light, protecting the user's eyes. The enemy prepares to fire, but just as the mantis catches the cicada, there is a sparrow behind. Deep in the jungle, a soldier using a third-generation night vision device already has him in his sights. The second-gen goggles struggle in extremely dark environments due to low photon counts, causing high image noise. The third-gen device uses a gallium arsenide (GaAs) photocathode, which is far more efficient at converting photons. However, residual gas in the vacuum tube can create heavy ions that bounce back and damage the cathode. To solve this, engineers coated the MCP input with an ultra-thin alumina film, allowing electrons to pass while blocking damaging ions. The enemy fires calmly and kills him. Finally, an enemy equipped with 4th-generation night vision technology watches silently. This device removes the ion barrier film and plates the oxide directly onto the inner walls of the microchannels to maximize electron throughput and eliminate the halo effect caused by the film. Since it cannot rely on an ion barrier, it introduces auto-gating power supply technology, which rapidly switches the cathode voltage on and off thousands of times per second. This prevents damage from high-energy ions and allows the device to instantly adapt to extreme lighting changes. Combined with a high-resolution white phosphor screen, it provides sharp, high-contrast grayscale images that reduce visual fatigue. When you throw a flashbang into the room, the auto-gating power supply instantly compresses the voltage to limit electron flow, so the screen only flickers slightly and returns to normal. You rush in for a sneak attack, but the enemy is ready, and you are neutralized. Do you know why? You can watch military commentary videos. If you want to see more popular military science content, you can follow me